In this video, we're going to learn how to solve equilibrium problems, and we can solve them in different ways depending on whether we know the initial concentrations, the value of the equilibrium constant, or the final equilibrium concentrations of the substances. So the first way we can solve for the equilibrium constant is using the equilibrium concentration. So we actually touched on this in our previous video. So in these examples, we're given the equilibrium concentrations of the products and the reactants. And in this example, we're being asked to find the value of the equilibrium constant at 25 degrees Celsius when we put 0.27 moles of iodine, 0.027 moles of chlorine, and 0.246 moles of iodine chloride into a 1 liter reaction vessel. So remember, we need to do these as concentrations. So in this example, conveniently, these are being placed in a 1 liter reaction vessel. So we don't have to calculate the concentrations because it's just going to be 0.027 moles per liter and so on. So the first thing you need to do is write the equilibrium expression, and then you can use the equilibrium concentrations to find the equilibrium constant. So the equilibrium expression would be the following. So Kc equals the concentration of ICl, and there was a coefficient of 2, so it's to the power of 2, divided by the concentration of iodine times the concentration of chlorine, and now we can plug in our values. So that's going to be equal to 0.246 squared over 0.027, and we can say that squared too because the concentrations were the same. Now we plug in those values, and our equilibrium constant is 83.01. Now, sometimes we don't know the equilibrium concentrations, but we can still find the equilibrium constant. So if we know the initial concentrations of the products and reactants, and we know the equilibrium concentration of one of them, we can solve for the equilibrium constant by using what is known as an ICE table to find the equilibrium concentration of all the substances. And then we can use those values to find the equilibrium constant. So in this example, 0.1 moles of nitrogen oxide, monoxide, 0.050 moles of hydrogen, and 0.10 moles of water are placed in a 1 liter reaction vessel at 25 degrees Celsius. So once again, we're using a 1 liter reaction vessel, so it's easier to calculate the concentrations. It's just 0.1 moles per liter and so on. At equilibrium, 0.062 moles of nitrogen monoxide remain in the flask. Determine the amount of water, hydrogen, and nitrogen in the flask at equilibrium, and then use these values to calculate C. So the first thing we need to do is set up what is known as an ICE table, and then we can plug our values in to find out the equilibrium concentrations of the reactants and products. So ICE stands for initial concentration, the change in concentration, and the equilibrium concentration. So remember, things happen in ratios with one another. So if something goes down by a certain value, other things with the same coefficient would also go down by the same value because they work on a 1-to-1 or 1-to-2 ratio and so on. So you would set up your rows like so, and then you would have a column for each of the participants in the reaction. And we will include the coefficients here to help us understand at what ratio or what magnitude these things are going to be changing. So we'll refer back to our problem, and we'll take a look and see that the initial concentration of nitrogen monoxide was 0.10. The initial concentration of the hydrogen was 0.050. We didn't have any nitrogen in the vessel, so that's 0. And we had 0.10 moles per liter of water vapor as well. So the only other value we know right now is the equilibrium concentration of nitrogen monoxide. So that was 0.062 moles per liter. Now we look and see how much the concentration in nitrogen monoxide changed between initial and equilibrium. So it went down by 0.038 moles per liter. So that means that the hydrogen also went down by that same value because they have the same coefficients. So 0.038. So that's going to equal 0.012 moles per liter. And then we take a look at nitrogen. It has a coefficient of 1, so it's going to go up by half of the amount of the other values. So it's going to go up, because we're producing that, by 0.019 mole per liter. So the total end concentration is 0.019. And then we take a look at water. It has the same coefficient as the others, so it's going to go up by 0.038. So we'll add those together. So it's going to be, the final equilibrium concentration is 0.138 moles per liter. So now we have our equilibrium concentrations, we can find out the equilibrium constant. So our next step is to use the equilibrium values to find the equilibrium constant, but the first thing we need to do is write the equilibrium expression. So the equilibrium constant is equal to the concentration of N2 times the concentration of H2O squared divided by NO squared times H2 squared. Now we can plug the values in. So that's going to equal 0.19 times 0.138 squared divided by 0.062 squared times 0.012 squared. And we calculate that, and K at equilibrium is 654. So this reaction is favoring the product, so it's proceeding more so in the forward reaction. So the final way we can calculate for these types of expressions would be if we had the equilibrium constant and the initial values only. We can then use those two things to find out the equilibrium concentrations of each. So in this example, we have carbon monoxide and water reacting to form hydrogen and carbon dioxide. And water is a gas, so we include this in the expression. So the equilibrium constant for this reaction is 10 at 693 Kelvin. 1 mole of carbon monoxide is mixed with 1 mole of water vapor in a 1 liter reaction vessel, which is convenient. We're going to use these values to determine the equilibrium concentrations of all the components. So our first step is to write the equilibrium expression. So Kc is equal to H2 times CO2 divided by carbon monoxide's concentration times water vapor's concentration. Luckily, all of these occur in a 1:1:1 ratio, so there are no exponents involved. Our next step is to construct an ice table again and to solve for the equilibrium concentrations. So in this case, we had 1 mole of each of the reactants and no moles of the products. Now, that's all we know, but we know that things will occur in ratios. So we know that carbon monoxide is going to go down by X, and so is water. But then the products are going to increase by the same magnitude. So they're going to increase by x. So then our equilibrium concentrations for these two would be 1 minus x. And these ones are just going to be x. So now we can put all our values into our equilibrium expression. So again, remember Kc is equal to H2 times CO2 divided by CO times H2O. So we can plug in our values now. So we know that the equilibrium constant is 10. That's equal to x times x over 1.00 minus x times 1.00 minus x. So the next thing we can do is condense that a bit, so simplify. That's going to be equal to x squared over 1.00 minus x squared. Rather than factoring, the easiest thing to do would be to take the square root of both sides to simplify this even further, because the opposite operation of squaring is square rooting. So the square root of 10 is going to equal the square root of these guys. So 3.16 is going to equal x over 1.00 minus x. So the easiest way to simplify this reaction would be to times both sides by 1.00 minus x. We can cancel over on this side, so it's going to be 3.16 minus 3.16x equals x. So then 3.16 equals, by taking the negative 3.16 onto the other side, it's going to be 4.16x. We'll divide, and x is going to equal 0.706. So now we have x, we can now plug in those values into our equilibrium concentrations. So remember, the concentration of carbon monoxide is also equal to the concentration of water vapor. So that's going to be equal to 1.0 minus x. So that's going to equal 1.00 minus 0.760, which is equal to 0.240 moles per liter. So those are our equilibrium concentrations for carbon monoxide and water. The concentration of carbon dioxide is equal to the concentration of hydrogen, and that's just equal to x. So that's equal to 0.760 moles per liter. So that took a little longer to solve, but there you go. We now know our equilibrium concentrations by knowing the equilibrium constant and the initial values. So now I'm going to leave you with one to solve. Hydrogen gas and bromine gas react to form hydrogen bromide gas. The equilibrium constant at a given temperature is 12.0. If 8.00 moles of hydrogen and 8.00 moles of bromine are placed in a 2-liter reaction vessel, find the equilibrium concentrations for all the materials. So a few things to note here before you go solve. The first thing is we have the equilibrium constant and we have the initial concentrations. So it's going to be the example that we just used to solve. But one thing to pay attention to is that it is a 2-liter reaction vessel. So you're going to need to solve appropriately. So you'll have to find the concentrations before you proceed with your solving. And also don't forget to write the proper balanced chemical equation so you'll know the coefficients. So have fun solving. I would like to note that the examples that are used in this video were adapted from the Cogni Higher Level Biology textbook.